Thank you, Christian, for the introduction. So I'm going to follow with a brief presentation of Symbio. So at Symbio, we make fuel cell systems for a wide range of vehicles, coming from light vehicles towards heavy-duty commercial vehicles. So today I'm going to focus about system architecture and especially the optimization of the hydrogen recirculation loop. So here's the agenda of today's presentation. I'm going to start off with a bit of context in order to understand the perimeter of the study. Then I will explain how we modeled our fuel cell system, and I will dive into detail for two critical components. And finally, I will explore some architecture optimization on the hydrogen loop. So today, fuel cells face two major challenges that are durability and efficiency. And for both of these points, we have targets that are given from the US Department of Energy. So the long-term target for 2050 is a peak efficiency of 72%, so this is an overall efficiency, and a durability of 30,000 hours. As an indication, today at Symbio, we sell fuel cell systems for heavy-duty applications with a durability of 20,000 hours. To reach these targets, the system is critical, and especially the hydrogen recirculation loop, because it has to provide first enough gas, meaning enough hydrogen in all the flow fields, all the cells, all the channels, and enough water to ensure water management. Also, it has to sustain the operating conditions that we define, so they are optimized to get the best performance and the best efficiency. And finally, the system has to do all of that while being compact, efficient, and lightweight. So on the right, here's an overview of the fuel cell system. So the stack needs air, needs hydrogen, needs some cooling, and it needs to be electrically controlled. So today, I'm only going to focus on the anode loop. So basically, it's composed first of a high-pressure supply, which is coming from the tanks. Then we have a recirculation. In our case, the recirculation is done with an ejector, but it could be also with a pump. And finally, we have the water trap and the purge. So in the first place, why do we need a recirculation? A fuel cell cannot operate at a stoichiometric ratio of 1, so we need to raise that. And an easy solution is to recirculate all of the exhaust gases that come out of the anode. So we recirculate hydrogen, but also contaminants such as nitrogen, and we recirculate water. So this recirculation helps the stoichiometry, but it helps also the water management by bringing water and by removing the excess water that is produced into the stack. So in our case, the recirculation is done with an ejector. It's a venturi, so it's compact, lightweight. It doesn't need to be powered. So this is a good solution. However, the sizing is critical, so I will dive into detail on that in the third part. And finally, with this architecture, the anode loop is a closed volume, so nitrogen and water will progressively build up and replace hydrogen, so they come from crossovers into the stack. They come from the air side towards the anode. And that's why we need to purge the anode regularly. So now that the system is defined, let's see how we modeled it. So here's an overview of the system with a focus, of course, on the anode loop. We can recognize all the components. And also we have the air loop, which is not detailed here, but it's mandatory in order to have the right boundary for the crossovers into the stack and for the purge. The key feature of the model revolves around crossovers, so we're able to predict nitrogen and water crossover, and so we can get the gas composition and the gas humidity. It's mandatory in order to know the anode stoichiometry, so how much hydrogen we have into the stack. Then, of course, we're able to assess the impact of the gas composition on the other components. So the gas composition will impact how the ejector works, and it will impact the stack pressure loss. Also, we have thermals, which are mandatory for humidity. And the geometry comes from a 3D conversion using GEM3D. The key outputs to study the anode loop are first the anode stoichiometry, but also the gas composition, the gas humidity, and the total stack flow rate for water management purposes. So let's go into detail on how we calibrated the stack. We used the provided template by GT, and we calibrated two major things: the anode pressure loss and the nitrogen crossovers. So I'm only going to detail those two. We used the provided multipliers, so two of them for the pressure loss and one of them for the crossovers. The result of the calibration can be seen on the graph on the right. So for the anode pressure loss, the result is quite good because the absolute error is at maximum 11 millibars, so it's quite low. And if we look at the relative error in the graph, we can see that it tends towards 0 at mid to high currents, so it's a very satisfying result. And the slight drop here, the slight error, needs to be minded for the future study. For nitrogen crossovers, we wanted to assess the sensitivity of the model to a pressure change, to a temperature change, and to humidity variations. So here you can see sensitivity plots towards temperature and pressure. And after the calibration, the model correlates really well to measurement, especially for temperature variation. We can see that we are really close to measurements, which is very satisfying. And for the crossovers regarding pressure, the sensitivity is also good, a bit less, but the maximum error is 15%. And on the usual operating range of the stack, it's even less, so it's a very satisfying result. The second critical component in our system is the ejector. We also use the provided template in GT, so it requires first a performance map, so how much flow rate is recirculated versus the different pressures around the ejector. And then the model is capable of extrapolating this performance towards different pressures, different temperatures, and different gas composition. So we got the performance map from testing in pure hydrogen, but we also wanted to calibrate and validate that the model is capable of predicting the performance of the ejector with a more realistic gas, meaning hydrogen, nitrogen, and water, which is usually what we have in the anode loop. So to do that, we used a CFD model of the ejector to create validation points and calibration points for the model. And the result can be seen here. So we assessed the sensitivity of the model to a variation of nitrogen from 0% to 20% in the anode loop. And we chose a gas constant exponent of 0.5. And we can see that the correlation between the CFD and the GT model is really good as well. So it's a very satisfying result. The only drawback is that the validation range of this calibration is a bit narrow, so we cannot go too extreme in terms of pressure. So now we have a calibrated model. It has been calibrated on a baseline system in order to get test data, which is mandatory. But now we're going to explore how we can improve the ejector sizing and then how we can improve the purge calibration. In order to study the ejector, I'm going to introduce the anode stoichiometry on the top right. So it's defined by the total amount of hydrogen coming into the stack divided by the amount of hydrogen that is consumed by the reaction. And usually, as I said, we go way above than 1 for the fuel cell. If you look at the graph on the left, we compared 3 ejectors on a polarization curve, so meaning the x-axis is the current. And we defined an optimal stoichiometry, so it's quite a complex number. It takes into account different things such as durability, flow repartitions. And ideally, we want to stay above this optimal stoichiometry to avoid any risk. So for the ejector number 1, which is the orange curve, we can see that it really works at low power. The anode stoichiometry is quite high at low power, however, it drops at high power, meaning that at maximum power, the stoichiometry is a bit low. And at the opposite, for the third ejector, which is a bit bigger, we can see that the recirculation works really well at high power. But we have a problem of idle power. So what is the idle power? Simply, it's the minimum power at which the system can safely operate. So it's the intersection between the curves and the green target. So with ejector number 3, the idle power is 50% higher than the first one. So it's not acceptable. The good trade-off is ejector number 2 because the idle power is still quite low, and we're able to reach maximum power with the optimal stoichiometry, so we do not risk anything on the durability side. So now that we've chosen the ejector, we can now optimize the purge, meaning we optimize what gas is left in the anode loop. So to do that, we defined the purge factor on the top right again. So the purge factor is basically the overconsumption of hydrogen due to the purge. A purge factor of 1.10 means that we lose 10% of the hydrogen at the exhaust due to the purge, and 10% is not acceptable, of course, for consumption. So we wanted to study how the purge factor influences the stoichiometry and the anode composition. We did a variation from 1 to 1.10, and we can observe the effect on the anode stoichiometry on the left and on the nitrogen consumption on the right. Basically, what we can see is the more we purge, the less nitrogen we have in the anode loop, and so the more hydrogen we have, which means more stoichiometry, which is great. So there is a trade-off here between durability and efficiency. And we can sense that this trade-off would be more interesting between 1 and 1.02, because in this range, a small variation of the purge factor will have a big impact on the anode stoichiometry. So we're able to gain some durability without losing too much consumption. So we carried out an optimization of this purge factor, taking into account different informations. So we optimize it differently at different current levels. So here we have the 3 current levels, 20, 200, 300. We can see the result of this optimization here. So we have, again, a polarization curve. And the initial setup is in purple. So we had 2 things to optimize here. In the first point, we can see that at mid-power, the stoichiometry is quite high. So we are able to lower the stoichiometry while staying in the optimal range, and so that we can improve the consumption because we lower the purge factor. So in point 1, we gain consumption and we don't lose anything in the durability. Point number 2, we want to improve the stoichiometry at low and high power so that we can reach maximum power without any risk for the durability. So but we've done that by raising the purge factor at low and high power. And we studied the impact on the vehicle consumption, and of course, this trade-off is studied to have as little impact as possible on the vehicle consumption. So now it's time to conclude. With this model, we were able to have a very satisfactory result for the calibration, and it allowed us to carry out virtual system architecture. So we were able to optimize our system, and the very next step should be to validate those results with a prototype on a test bench. Also, another outlook would be to add a bit more complexity, especially on the crossover side, to have a better calibration of the stack. Thank you for listening, and if you have some questions, feel free to ask.
Yeah, thank you, Emilien, for the interesting presentation. Are there any questions from the audience? If not, maybe I can start with one question. I don't know how much you can share about that, but especially for the purging design. So what is your strategy for controlling the purge? So is it just purely time-based or kilowatt-hour based, or can you share anything about?
Well, I didn't talk about it in details, but yeah, in the model we studied a continuous purge, so it's like a bleed. But of course, this model will allow us to study how we're going to calibrate it. So continuous purge or discontinuous purge, meaning with a frequency of X seconds. So it's in the pipes.
Okay, so still a lot to do. Yeah.
Hello, Stefan Bohacz from PowerCell. You mentioned the nitrogen crossover. Did you investigate the water crossover as well?
Yes, we investigated water crossover. It was a little bit harder to get test data from that. So the calibration regarding water crossover was less precise than the nitrogen crossover. We looked at the humidity in the anode loop, actually. But we didn't got any trouble to calibrate that. So.